Hey, welcome to the team. I am absolutely thrilled to have you on board with us. Now, if you're sitting there looking at our code base, wondering how all the pieces of our infrastructure actually fit together, don't worry, you are in the exact right place. Consider this explainer your ultimate onboarding guide to our core intelligence system, the end-to-end RAG pipeline. We're going to break down exactly how we orchestrate a really complex, step-by-step journey, transforming a simple user query into a highly accurate, context-aware answer, and doing it all in a fraction of a second. So grab a coffee, get comfortable, and let's dive right into this. All right, here is our roadmap for today. Section 1, RAG is a coordinated pipeline. Section 2, the query's high-speed journey. Section 3, refining context and ranking. Section 4, generation and continuous feedback. Section 5, balancing production system trade-offs. And finally, Section 6, the weakest link principle. Think of this outline as the architectural blueprint for a very high-speed roller coaster ride through a complex information space. Okay, kicking things off with Section 1, RAG is a coordinated pipeline, moving beyond isolated models. Look, we've got to shift our paradigm right off the bat here. The biggest myth new developers tend to believe is that building a RAG system is just about, having a really great embedding model, or standing up a blazing fast vector DB, or just calling a massive LLM in a single-step, one-shot request. But let's be real. Imagine asking a system to do a full Q3 expense analysis in one shot. No way. It would hallucinate wildly because it completely lacks structure. The reality is that true end-to-end RAG requires multi-step workflows. It's about coordinated system design where using planners dramatically reduces errors compared to those one-shot requests, simply by breaking down the complex task. It's an optimized flow where data moves seamlessly from component to component, continuously refined by feedback. I want you to literally burn this quote into your memory. RAG is a pipeline, not a model. This kind of hierarchical structure is absolutely essential for building scalable intelligent systems. Think about it. When a user asks our system to analyze those Q3 expenses, we don't just blindly throw it at a single model. We perform effective task decomposition. We execute a very specific list of actions, first parsing the user's intent, then filtering out all the irrelevant noise, retrieving the exact financial records needed, and finally logically synthesizing that data. Adopting this pipeline mindset right now is going to make your code so much more resilient. Moving on to Section 2, the query's high-speed journey, from input to retrieval. So now that we've got the right mental model, let's actually follow a query, like summarize Q3 travel expenses, from the exact moment it hits our API gateway. What's mind-blowing here is the sheer speed. We are operating strictly in the microsecond domain. At 0 milliseconds, the query arrives. Boom. By 10 milliseconds, we've already passed that text through our embedding models to generate the vector representations. At 50 milliseconds, we are deep inside the vector DB, executing an approximate nearest neighbor, or ANN search. And bam, by 100 milliseconds, the retrieval layer has successfully pulled the top K results. It's a lightning-fast journey through a massive amount of data. But, and this is a big but, as fast as this is, those top K results are basically raw, unrefined ore at this stage. They need serious processing. Which brings us nicely to Section 3, refining context and ranking, the precision filters. Fast retrieval is awesome, for sure, but raw search results often contain a lot of noise. We have to heavily refine this data before it ever even touches the final language model. Enter the reranker. This is our precision filter. A reranker, which around here is very often a cross-encoder, takes those top K documents we just retrieved so fast and meticulously evaluates them against the original query. It performs score fusion to drastically improve the ranking quality before we move to context engineering. Think of the vector DB as casting a really wide net incredibly quickly, and the reranker as the expert sitting on the boat, sorting through that net to find the absolute highest value catches. The workflow in this layer is what literally secures our accuracy. Step 1 is that re-ranking we just talked about, but Step 2? Step 2 is equally vital, context engineering. We don't just dump a massive wall of raw text into the LLM. We perform context compression and formatting. You see, the context window of an LLM is prime real estate. It is super expensive and strictly limited. Context engineering ensures that only the absolute best, most relevant, and perfectly formatted information reaches the generation layer. This drastically reduces hallucinations and keeps our prompt sizes totally optimized, especially when we're dealing with hundreds of messy expense reports. Let's jump into Section 4, Generation and Continuous Feedback, Advanced Features and Final Polish. All right, we've finally reached the stage where the answer is actually constructed, and this involves several advanced architectural features.
This is exactly where our team's architecture is heading right now and where you'll be contributing on day one. We use hybrid retrieval, blending semantic vector search with traditional keyword-based BM25 to basically get the best of both worlds. We use multi-stage ranking, flowing from the ANN search to the reranker, and finally to the LLM. Our pipelines are adaptive. That means we dynamically change the K value of retrieved documents and adjust context sizes on the fly based on how complex the query is. And crucially, we maintain a continuous feedback loop and a strict security layer guarding against prompt injections. The LLM isn't just out there generating text in the wild, it's operating within a highly controlled, secure, and self-improving orchestration flow.
Okay, Section 5, Balancing Production System Trade-offs, Navigating Engineering Realities. Now, here's where theory violently meets reality. Building this pipeline is all about making hard engineering decisions, and this matrix right here is going to be your absolute best friend. In the retrieval layer, we trade recall against latency. We might want to add some guidance on tuning parameters like increasing search depth for better accuracy when finding those expense docs, but we literally can't make the user wait 10 seconds for a database scan. In the re-ranking layer, it's a battle of accuracy versus speed. For the context layer, we are constantly balancing completeness against strict token limits. And at the LLM generation layer, well, it's the classic quality versus cost debate. As an engineer on this team, your main job is to constantly tune these exact dials based on our changing system requirements. And because those trade-offs are genuinely hard, mistakes definitely happen. I want to point these out right now so you feel fully supported in navigating them. The most common production mistakes we see include optimizing only one component in a vacuum, like say spending 3 weeks tweaking the embedding model while totally ignoring that the LLM is receiving horribly formatted expense data. Another big one is ignoring latency, which results in a system that is incredibly smart but completely unusable because it's so slow. Then there's having no feedback loop to actually learn from bad answers. And finally, poor context construction. Recognizing these pitfalls today will save you a massive amount of debugging time later. Finally, we hit Section 6, the weakest link principle, defining overall system quality. As we wrap up this explainer, I really want to leave you with this ultimate takeaway. The weakest component defines your overall system quality, period. This is just a stark, undeniable reality of pipeline architecture. You could have the most perfect, state-of-the-art embeddings in the world and a 1 millisecond vector DB. But if your context construction is bad or your re-ranker accidentally drops the most important documents, you are going to get a bad answer. The end user doesn't care at all how fast our database is. They only care if their final generated Q3 expense analysis is actually correct. Which brings us to our final thought for you to chew on. If your LLM gives a bad answer, what part of your orchestration pipeline actually failed? Was it the retrieval recall? Was it the re-ranker's precision? Or was the context truncated somewhere along the way? Answering that question requires diving deep into our evaluation metrics like recall at K and NDCG, tracking the logs, and monitoring overall system health. That right there, that is the real work of engineering a true end-to-end RAG system. I really hope this explainer gave you a clear, structured view of the multi-step journey ahead. Get your dev environment all set up, and let's get building.